All right. So I'm just going to be doing example problems. I'm going to start with example 3-7, and this example is to determine the temperature of water at a state. Determine the temperature of water at a state of 0.5 megapascal and an enthalpy of 2,890 kilojoules per kilogram. So I'm going to give you a few minutes to try to solve the problem yourself, and then I will go over the answer. So determine the temperature of water at a state of 0.5 megapascal and an enthalpy of 2,890 kilojoules per kilogram. So I'll give you about 5 minutes to work on that yourself, and then I will go over the answer. I'm going to go get a tissue to blow my nose in the meantime, so 5 minutes. All right, so it seems like a few people have already gotten an answer, so I'm going to go ahead and go over it. So Christian 216.25 is correct. So how did you get that answer? Yep, so the trick to this question is interpolation. We went over this right before the first exam, so good job. We have our pressure as 500 kilopascals or 0.5 megapascals. And if we look at 0.5 megapascals, and then our enthalpy of 2,890 kilojoules per kilogram. If we were to look at table A5, which is kind of our comparison point, our starting point, if we were to look at our set pressure of 500 kilopascals or 0.5 megapascals, the enthalpy of our vapor, so our top enthalpy here, would be 2,748.1 kilojoules per kilogram from table A5, which is our saturated liquid vapor. And since our H value is larger than this saturated vapor value, then we know that we have a superheated vapor. The heat content is higher than our saturated vapor, and this means that we're going to need to go to table A6. So when we go to table A6, we see that there is our at pressure 0.5 megapascal, we have our temperature, and we have 200 degrees Celsius and we have 250 degrees Celsius. Well, you could use HF, but HF is your saturated liquid. So we know that we're definitely going to be higher than our saturated liquid. So the enthalpy of your saturated liquid is always going to be lower than the enthalpy of your saturated vapor. So knowing that you're comparing a superheated vapor to a saturated vapor is part of the problem. So if your enthalpy value for your saturated liquid is higher than your enthalpy for the problem, then you're probably in a compressed liquid or maybe a saturated liquid vapor, like a lower region. But if your enthalpy is higher than your saturated liquid, then you would need to compare it to your saturated vapor, and then you would need to compare it and figure out that it's a superheated vapor. So you know to compare it to your higher value to determine a superheated vapor. So the temperature in your table A6, which is your superheated vapor table, you have at pressure 0.5 megapascal, you have your temperature of 200 and 250, and you have your enthalpy in your kilojoules per kilogram of 2,855.8 and 2,961.0. So we know that our temperature is somewhere in between here because we have an enthalpy value of 2,890 kilojoules per kilogram. And we can see just by looking at this, we're probably going to be a little closer to 200 than 250, just because 289 is closer to 2855 than 2961. But it's not going to be so close that we can just say, oh, this is about 100. We're going to need to do interpolation. So here's where we have to do interpolation. If you remember, interpolation was the equation y equals, and this can be y3 equals y1 plus x3 minus x1 over x2 minus x1 times by y2 minus y1. And here your y's are always going to be your unknown. So your y3 is going to be your unknown temperature. and your x3 is going to be 2,890. So plugging and chugging this in, you get your temperature to be 216.25 degrees Celsius, which makes sense because that number is between 200 and 250, and it's a little bit closer to 200 than 250. Any questions? All right, so I have another problem that is long that we are going to do. So this problem is long. I'm just warning you. It provides a lot of information and shows a lot of examples, but it's a long problem. So a spring loaded piston cylinder device is filled with a spring-loaded piston device cylinder is filled with refrigerant R134A. It's filled with refrigerant R134A. The water. Oh, nope, sorry. Well, that's stupid. In the problem statement, it says your piston is filled with refrigerant, the water, even though you were just told it's refrigerant. So we're going to say the R134A, that's a mistake on their part. The R134A undergoes was that to me, or does somebody just think they're on mute and they're not? Okay. The water undergoes a process until its volume. The water undergoes a process until its volume is increased by 40%. Is increased by 40%. The final temp and enthalpy are to be determined. Bless you. The final temperature and enthalpy are to be determined. The initial system is at negative 34 degrees Celsius. The initial system is at negative 34 degrees Celsius and 80% vapor. The system is 100 grams total. The system is 100 grams total. The spring constant is 6.6 kilonewtons per meter. The spring constant is 6.6 kilonewtons per meter. The piston has a diameter of 0.3 meters. The piston has a diameter of 0.3 meters. All right, so there is the problem. So we have some sort of cylindrical device, so some sort of sphere. I'm sorry, not sphere, a cylinder, cylindrical device. And we have a piston inside this device that can move up and down. So our volume can change based on how the piston moves up and down in here. And this piston coming in is spring loaded. So this isn't the best drawing I've ever done, but this is a spring loaded piston. So our spring here has a spring constant of 6.6 kilonewtons per meter. We know that this piston area is equal to the diameter times pi divided by 4 squared. So pi diameter squared over 4. We know that this is filled with R134A. We know that its mass total, initially at least, but I don't think we're going to be losing any mass because we're not doing mass transfer in this class, is 100 grams. We have our initial starting temperature as negative 34 degrees Celsius. We know that our change in volume is going to be 40%. We want to find our final temperature and our final enthalpy. I shouldn't label them as T sub F because that looks like T sub saturated liquid. So I'm going to say temperature final and enthalpy final. We're told that we have 80% vapor, which also means that we are a saturated liquid vapor, initially at least. So our initial quality is 0.8. And this also determines that we're a saturated liquid vapor because the term quality, that means that we're a saturated liquid vapor. I believe that's all that we know from our starting problem statement. All right, so we want to figure out temperature, and we have a lot of stuff that is given to us. So kind of figuring out like what equations that we need for temperature is a little intimidating. So I'm going to give you like just a second to figure out like what equation you would start with, where you would even start, what's the first thing that you would do. And then I'll show you what the first thing I would do, and you can kind of see if those mesh or if maybe they don't. So just a minute to think about what you would start doing. All right, so the first thing that I would do is I would say, well, I know that I'm a saturated liquid vapor. So yeah, we know this diameter here. So I guess we one of the other things that we know is that this diameter is 0.3 meters. So one of the things that we're looking for is temperature. One of them is enthalpy. We don't know anything about pressure, but we are given an initial temperature, and we do know what table we're going to use. So one of the first things that I would do is find my pressure initial, which is going to be equal to my saturation pressure at negative 34 degrees Celsius from table A11. And so when I look up negative 34 degrees Celsius, my saturation pressure from table A11 on page 916 in the 8th edition, and page 900 in the 9th edition, I can find that my corresponding pressure is going to be 69.56 kilopascal. So now I know pressure. I know my initial pressure, but I don't know my final pressure. So in order to determine anything about my final situation, I would need to find my final pressure. The way I could find my final pressure is by looking at this spring piston. So we have an equation for pressure that is associated with a piston, and this is the change in pressure is equal to the change in force over area. So force over area is pressure. This is an equation for pressure. I'm assuming that you've seen this in Physics 1, which is a prereq for this class. This might be on the memorized sheet. If not, add it. Pressure is force over area. That's just something that you should know. And with a spring, our force becomes our spring constant times our change in like the distance the piston moves. So this is our spring constant. Okay, stress equals force over area. Our change in pressure here is going to be our change in force over area. Stress and strain are like specific to certain types of problems, but that's fine. So just remember that change in pressure can also be a stress depending on how it's being applied. And it's the change in force over the change in area. So here's our spring constant, which we were given. And then this delta X is the distance the piston moves. Distance piston moves. So we know our piston area, right? We know our spring constant, but we don't know the distance that the piston moves. So what variable does this piston movement correspond to?
Change in volume.
Right. So now we know that we need to figure out our change in volume. What are these actual volume values, volume numbers, to determine this change in piston movement? So now we're going to go back to our table and try to determine from table A11 at negative 34 degrees Celsius what our specific volumes are for our saturated vapor and our saturated liquid. So on page 900 at negative 34 degrees Celsius, we have our, I'm going to put this as number 1. I'm going to put this as number 2. At table A11, we have our specific volume values. So our specific volume of our liquid, our saturated liquid, is 0.0007141 cubic meter per kilogram. And our saturated vapor is equal to 0.27082 cubic meter per kilogram. So these are our initial values at negative 34 degrees Celsius. We'll have final values at some other given temperature, but we don't know what that temperature is. We do know that our volume changes 40%, so we can work with that value. I'm gonna need more space, so I am going to delete this once everybody has it copied down. So let me know if you need more time. All right. So we know that our specific volume of the fluid, saturated liquid, is 0.0007141 cubic meter per kilogram. And we know that the saturated vapor specific volume is going to be 0.27082 cubic meter per kilogram. I'm just copying that from the last page. If we want our specific volume initial, our overall specific volume initial, this is where we're going to have to use the equation of our specific volume of our saturated fluid times our quality plus the quality times our specific volume of our saturated liquid vapor region. And these are all our initial values. So our initial value for all of these specific volumes and quality at negative 34 degrees Celsius. So at T equals negative 34 degrees initial temperature. So we have values for the saturated liquid. How do we get our value for our saturated liquid vapor region?
The gas minus the fluid.
Yep. So we have our saturated vapor or liquid plus our quality times the specific volume of our vapor minus the specific volume of our fluid. And now we have these values that we looked up in the table. We have this value that we looked up in table A11. And then we were given our initial starting quality as 80% vapor or 0.8. So now we can just plug and chug. So 0.0007141 cubic meter per kilogram plus our initial quality is 0.8, 80% liquid. And then our specific volume of our vapor is 0.2709 or 0.82. And the specific volume of our liquid is 0.0007141 cubic meter per kilogram. So the units that we should be left with, quality is unitless, it should be cubic meter per kilogram. We're trying to get an initial specific volume. So we can just plug and chug. I got this value to be 0.2169 roughly. I'm kind of rounding a little bit, cubic meter per kilogram as our initial specific volume. So, all right, now we know our initial specific volume, but we can't really do much from there. So we need to figure out where to go to next. And one of the things that we're given is that our change in overall volume is 40%. So this would be our volume final minus our volume initial is equal to a 40% change. So another way of looking at this would be that our volume final is equal to 1.4 times, I'm sorry, I don't mean that delta in front. Just our plain volume final is equal to 1.4 times our volume initial. So it is 140% of our volume initial. So it is the entire initial volume plus an additional 40%. So a 40% increase, a 40% change from our initial. 1.4 is this 40% change. So it's not 40%. Our 40% change in the problem statement, we're told that the volume of the process is undergone until the volume is increased by 40%. So it doesn't start at 0 and then go to 40. It starts at what it is and then increases 40%. So we have the entire volume that it already was, a value of like 1, and then, or 100% of what it is, right? That's what it's starting at. And then it's increasing an additional 40%. So 1.4 is the entire value that it was, 1, and then plus an additional 40%. So if we just made this a 0.4, we're actually saying that it's 40% of the initial volume, but it's not. It's the entire initial volume plus a 40% increase. So this is essentially like 1 plus 0.4 times our initial volume is equal to our initial our volume final. All right, so now since we know that we want to figure out our volume final because we want to get our temperature final, our enthalpy final, we want to be able to look these up in a table. And because we also want to know this, the amount that the piston cylinder moved for solving our pressure equation, then we are going to want to figure out our volume initial, which is going to be equal to our mass initial times our specific volume initial. And so our initial mass, we're told, is 100 grams. And our initial volume is what we just calculated. Since this is in kilograms, 100 grams is 0.1 kilograms. And then multiplied by our volume initial, which is 0.2169 cubic meter per kilogram. The kilograms are going to cancel. We're left with cubic meter. That's a volume. So that is good. So our volume initial is 0.02169 cubic meter per kilogram. Oh, no, not per kilogram, just cubic meter. Got carried away. Too much specific volume. And then we know that our volume final is equal to 1.4 times our volume initial. So 1.4 times 0.0219 cubic meter is equal to 0.003036 about. No, yeah, 36. No, there's too many zeros. Oops. .38. Okay. 0.0. Like I said, I do this all on my iPhone calculator, so there might be some minor mistakes. 0.030. Let me do it again. 1.4 times 0.2169. No, I got 0.0. 0.03036 cubic meter. Did anybody else get that? Okay, great. Yeah.
I got that. I got that too, but I have a quick question about the change in volume. If the piston's moving downwards, aren't we decreasing volume by 40%?
Yes, but in the problem statement, it says the volume is increased by 40%. It never says the piston moves downwards.
Okay, sorry about that.
So the piston is moving up.
Okay, got it.
Other questions? Okay, so now we know that our volume final is 0.030366 cubic meter. And if we want to get our specific volume final, then our specific volume is our total volume final divided by mass final. So our volume final is 0.030366 cubic meter. And our mass final is still going to be that 0.1 kilogram because we are not losing any mass. We don't have any mass transfer occurring. So this becomes 0.003036 cubic meter per kilogram as our specific volume final. All right.
What's that number? Oh, sorry. To the very left of the page on the very bottom for V final, what's next to V initial in terms of numbers?
Right here.
Yeah.
This is 1 plus 0.4.
Okay, thank you.
Other questions? All right, so we know that for our piston, we have our change in pressure is equal to our change in force over area, which was equal to our spring constant times our amount that the piston moved divided by area, which is going to be pi d squared divided by 4. And we know that the piston, the area moves is equal to the change in volume over the area. So that makes sense, right? If you're looking at a piston, the amount that the volume moves over the amount of area is going to equal that delta x term. So the change in volume over the change in area. We already know the change in volume from everything we did on the last page. We know that our area is going to be the same as this piston area. So now we have our change in volume over our pi d squared over 4, which becomes 4 times the change in volume over pi times d squared. We know our change in volume and we know our d. We can plug and chug. So we have our 4 times our change in volume, which is our volume final minus our volume initial. So our volume final, our total volume final was 0.03066 cubic meter. And our volume initial was 0.02169 cubic meter. Our pi value and then our diameter is 0.3 meters. That was given in the problem statement, and we need that squared. So I got this to be 0.123 meters as our change in x. So now we know our K value, it was given in the problem statement. We know our change in X and we know our D. So we should be able to plug and chug for our change in pressure equation. So now we have our change in pressure is equal to K delta X over pi D squared and then times 4. So here we have our K as 6.6 kilonewtons per meter, our delta X as 0.123 meters, our pi value, and then 0.3 meters squared again, and then times our value of 4 that I'm just moving up from the denominator down here. So our meter squared will cancel with our meter squared here, and we're going to be left with, wait, that's not right. They won't cancel.
Cancel up there.
Say that again.
The mass will be canceled up.
Yeah, these cancel, but this meter squares remained. Is that what you were saying?
Past kilopascal.
Right, yeah, so then you get kilonewton per meter squared, which is kilopascal. So the meter here will cancel with this meter here, so we're left with kilonewton per meter squared, which is kilopascal, which is a pressure term. So when we solve all this out, I get 11.5 kilonewtons per meter squared, or 11.5 kilopascal as our change in pressure. I guess I don't need to box that, but just because I feel like we did a lot of work to get there. All right, so our change in pressure is equal to our pressure final minus our pressure initial. We just figured out our change in pressure, and we know our pressure initial because this is what we looked up at negative 34 degrees Celsius. So now we're able to solve for our pressure final. Our pressure final is equal to our pressure initial plus our change in pressure. And our pressure initial was 69.56 kilopascal. And our change in pressure was 11.5 kilopascal. So our pressure final is going to be 81.06 kilopascal. All right, so now we have our pressure final as 81.06 kilopascal. And we have our volume, our specific volume final as 0.0030366 cubic meter per kilogram. So we can go to our tables and find what our temperature and enthalpy values are associated with this pressure and this specific volume. So instead of using table A11 right now, we're going to use table A12 since we're looking at pressure as our main first column instead of temperature. So this is going to go to table A12. It's still saturated liquid vapor, but it's for our first column is pressure. So if we go to 81.06 kilopascal, I'm going to say that this is about 80 kilopascal because I don't want to do interpolation right now and they're very close. So I'm going to say that this is about 80 kilopascal. And so therefore my temperature is negative 31.13 degrees Celsius.
For the VS final, the specific final volume, didn't we do the final volume divided by 0.1 kilogram?
Yeah, that's what I thought, and I had it at 0.304, not
Yeah,
0.00.
I think you multiplied instead of divided when you got that one.
Um, so when I had my specific volume final is 0.030366 cubic meters. And the definition of specific volume is volume over mass.
Right, and then you divide it by 0.1.
Oh, you're right. Oh. So this should really be 0.3036 cubic meters, but that does not work for the problem. Because that is that specific volume is larger than the saturated liquid vapor specific volume for saturated vapor, which means it's a superheated vapor, but it's not. So
But you were using the density, which is mass over volume. And from that, if you add the density, you could get the volume out of it.
no, there's more of a, well, possibly, but I don't know the density of R134A, and I don't, the volume shouldn't be different doing it that way. I think I'm gonna have to add an amendment to the problem statement. Okay. So, what we're gonna have to do is on the initial problem statement, the mass final, the final mass is gonna have to be what, 10 kilograms to give us the same value. So our mass initial is 100 grams and our mass total is 10 kilograms. So we're adding refrigerant to the system.
Any problems you give us won't have this issue though, right?
No, no. So
So for like the initial setup, are we just changing MOT?
So your MT just becomes your MT initial, and then your MT final is 10 kilograms. So it makes me feel a little better. Like this is a problem from your book, and they wrote that as the solution. So that wasn't my bad math. This is problem 333 from your book, and that's the mistake that they made. And that's why I'm not just like saying, oh, we can fix it, because I know what the rest of the problem looks like. So in the initial problem statement, we need to make that the final is 10 kilograms.
And the 100-gram becomes the initial total.
Yes, yeah, so our M initial is 100 grams. Because you still need it for your initial specific volume. It's just your final specific volume that changes. But if you look at your table in your book, your pressure at 80 degrees, if you look at the specific volume, your maximum saturated vapor specific volume is 0.23749. So there's no way that this can be 0.3. It doesn't make sense. It's not possible. So we definitely need it to be this 0.0036, because this is much closer to our saturated liquid vapor region, and it's much closer to the saturated liquid region. There's another reason we need it that I haven't like gone over yet. So gonna change this so I can change the notes. All right, so in the problem statement, no, the temperature is negative 31.13 degrees Celsius. This is from table A12. In the problem statement, your mass total initial equals 100 grams, and your mass total final equals 10 kilograms. All right. So now we know temperature because we were able to look it up, but we still want to find enthalpy. So if we were to look up enthalpy, we, on the same line, we can find that our enthalpy of our saturated liquid is equal to 11.14 kilojoules per kilogram. And our saturated liquid vapor is equal to 212.48, is that right? No, 220.27. 220.27 kilojoules per kilogram. And our saturated vapor enthalpy is 231.47 kilojoules per kilogram. So we don't really know what enthalpy to choose, and it's probably based on our specific volume, which is between our saturated liquid and our saturated vapor. It's probably going to be a value somewhere in between here. But we don't really know how to find that without using the equation where our enthalpy is equal to the enthalpy of our saturated liquid plus our quality times the enthalpy of our saturated liquid vapor. But we don't know our final quality. we only know our quality initial, which was 0.8, but we don't know our final quality. So while we have these two values, we don't know what our quality is. So our quality is equal to our mass of our vapor over our mass total, but we don't know what the mass of our vapor is at our final stage. So we also know that it's equal to our specific volume minus the specific volume of our saturated liquid over the specific volume of our saturated liquid vapor. So we have all of these values and we can plug those in. So and this is quality final. This is our final quality. So we know that our specific volume is 0.003036 cubic meter per kilogram. And our specific volume of our fluid, our saturated liquid, was 0.0007184 cubic meter per kilogram. And our saturated liquid vapor is going to be our saturated vapor minus our saturated liquid, which is 0.2702 cubic meter per kilogram and 0.0007184 cubic meter per kilogram. No, it's not, there's no zero here. It's 0.27802. Yeah, that one. So all right, so I think when I type this in, I got about 0.01, but I'm going to try it again because I want to double check. Yeah, it's roughly 0.01. So 0.009, 0.001. Any of those are fine. They're small enough that it's not going to make a huge difference. So I actually got close to what Christian got, 0.0086-ish. So we can just use 0.009 or 0.01. So now we can come back up here. We know that our enthalpy is equal to our enthalpy of our saturated liquid plus quality times enthalpy of our saturated liquid vapor. We know that the enthalpy of our saturated liquid is 11.14 kilojoules per kilogram. Our quality here is 0.009, 0.1, 0.0086. I wouldn't take off points for any of those. And then our enthalpy for saturated liquid vapor is 220.27 kilojoules per kilogram. And if we put all these together, we get $13.12 kilojoules per kilogram, which is our enthalpy final of our system. So now we have our final temperature and we have our final enthalpy. Yeah, it's a long problem, especially when the problem statement misses out important information. So yeah, it's a doozy. It's a long one. I wouldn't ask one like this on an exam, but I think it shows you how to use the tables, how to use specific volume, how to use quality, how to use like all these important factors. So I think, hold on one second. All right, so I think it's a pretty good problem. Are there any questions? Okay, so on Friday, we're gonna practice more, and then next week we start chapter 4. So make sure that you finish reading chapter 3, make sure that you feel comfortable doing these problems on your own. And I will see you all on Friday. We'll have problem solving again, like usual. So everybody have a good day, and I will see you on Friday.
Thank
I have
you.
a question, Professor.
Yes, go ahead.
If on a problem I'm working on, I was given I'm working for water, where I was given only the temperature, and I'm giving the phase description, and it says saturated vapor. We don't have a table with saturated vapor. We have superheated. So can I use the superheated to find like the pressure and the energy?
No. So if you are told that you have a saturated vapor, this means that you are in the saturated liquid vapor range. So if you remember this table or this graph where we have the compressed liquid, we have superheated vapor, but this entire range is our saturated liquid vapor range, and it starts with our saturated liquid and it goes to our saturated vapor. But this is in table A7. If this is water, this is table A4 and A5. And this is table A6. So you can only use your superheated vapor table when you for sure have a superheated vapor. If you have a saturated liquid, so anything with the subscript F, if you have a saturated vapor, which is anything with the subscript of G, you have to use the saturated liquid vapor tables. Anything that's in between these two has a subscript of FG. So if you're told that you have a saturated vapor right here, you have to use the values that have a subscript of just G in your saturated liquid vapor tables, which are table A4 and table A5 for water.
So that would be table A4 or 5.
Yes. So those are your, I think it's called like saturated water table or something. But
Yeah,
it's
saturated
table A4.
water. Yeah.
Yep.
And there's no extrapolation on that. Just get any value in between that interval.
So you might have to do interpolation based on what you're looking at. But if you're told that you have a saturated vapor and the temperature is, 50 degrees Celsius, what's the internal energy? You can just go to your 50 degrees Celsius line, read across, look at your internal energy for your saturated vapor, and then copy that value down. But if you're given something like 52.7 degrees Celsius, you're going to need to do an interpolation between 50 and 55 degrees.
Also, yeah, if I have the exact temperature, I can just use the one that's given on the table as the actual.
Yeah, if you know that
okay.
your entire thing is saturated vapor, you can just use that value. If you know you're entirely saturated liquid, you can use this value. If you don't know if you have a mixture, here's where you have to use the equation that includes quality.
Okay. Thank you.
Yeah. Any other questions from anybody? All right, well then have a good day. I'll see you on Friday.
Thank you.